In this video, we're going to evaluate this integral. The form it's in right now, there is no way to evaluate it, but we're going to do this, or at least try to approach it, using the Lebon's differentiation technique of integrals. We've got a couple examples now of how, when we have an integral such as this, that we have no way to integrate it. Sometimes when we can differentiate the integral, that will give us a path to go back to the original expression and find a way to evaluate it. So that's what we're going to do in this video. The playlists are at the website digital-university.org. If you go there and click where it says free calculus videos, then when you're in that section, scroll down to where it says differentiation of integral functions. And we spent the first 3 videos in that section. They were devoted to developing Leibniz's general formula that we have right here. And this is what we're going to use to differentiate this integral and see if we can find a solution for it. So we have e to the minus xt, then we have minus, this is e to the minus yt divided by t. So we can split this into 2 different integrals if we want. This would equal e to the minus xt over t dt. T goes from 0 to infinity, minus e to the minus yt over t dt. Now, if we could integrate this, it would come out as some function of x. When we integrate it, initially we'd have a function that would have x and t in it, then we would substitute 0 and infinity for the t's, so you'd have only a function of x remaining. So this is some function I of x, and again, we've discussed this in more detail in the previous videos in this series. This would be some function I of y, now if we try to take the derivative of this integral with respect to x, the first thing we do is take the differentiation process inside of the integral. That's this step right here. Hopefully everyone is familiar with this after we went through and developed this entire formula. So here then, we're taking the derivative of an integral with respect to x. Now we just take the differentiation process inside of the integral. Now, for this general case, the limits are functions of x. For our problem, they're constants, so this derivative and this derivative are 0. So to get the derivative of the integral, we have only this first term that we have to deal with. And again, that's because with our problem, we have constants as our upper and lower limits on the integral. So this will equal and now we'll say taking the partial with respect to x, because this is a function of x and t, so we have e to the minus xt divided by t dt. Let's write it like this to be clear about this. So we have to take the partial of e to the minus tx over t with respect to x. So this will equal the integral, we'll have 1 over t, and then the derivative of e to the minus tx with respect to x, we will have e to the minus xt, and then taking the differential here, that will be minus t. So we'll have minus t, and then we have dt. So this will equal, of course this is just 1, so we have minus the integral from 0 to infinity e to the minus xt dt. This is just 1, so you have minus e to the minus xt dt. Now when we integrate, we just treat x as if it's a constant. So this equals minus, then here we'll have minus 1 over x e to the minus xt, where t goes from 0 to infinity. So this would be plus 1 over x. When t is infinity, this is e to the minus infinity, or that's 1 over e to the plus infinity. That's 0. When t is 0, e to the 0 is 1. So this equals minus 1 over x. So our first integral was this one, and the derivative of that with respect to x is minus 1 over x. So what we're doing now is the integral, we're just calling that I, and we're treating the I right here just as a variable, taking its derivative, following the rules by taking the derivative inside the integral and going through the steps, and we end up with minus 1 over x. So we have di of x equals minus 1 over x, di of x dx. That's what we get after we go through all of these steps. So let's get this stuff out of the way. And again, the steps themselves are pretty straightforward. But what's unusual is that here we have this expression the derivative of an integral, the derivative of this integral with respect to x equals this. Now we can multiply both sides of the equation by dx, and we have, just treating now, this actually stands for an integral, this one, but we're just treating it as a variable. This equals minus dx over x. So just treating this as a variable, we can integrate each side, and we'll have I of x equals minus the natural log of x plus some constant. So, but what is I of x? It's this integral. So what we've established so far is that the first integral, 0 to infinity, of e to the minus xt divided by t dt equals minus the natural log of x plus an arbitrary constant of integration. So this is what we have for this integral. So let's make some room and deal now with this integral, because this one is almost identical. We have minus y instead of minus x, and there's a minus sign before it instead of a plus sign. So here, let's just write this equals minus ln of x plus c1. Now for this one, if we go through exactly the same process, we're going to have that this integral I of y equals plus the natural log of y plus a different constant of integration. It's exactly what we did with this one, except we have a y and an x, and this with a minus sign here gives us a plus sign here before we had a minus sign here. Other than that, they're identical. So what we have then is going back to our original integral here, e to the minus xt minus e to the minus yt divided by t dt equals this minus the natural log of x plus c1 plus from this integral, which is this, plus the natural log of y plus c2. Or we can write it like this. Combine these together, that's the natural log of y over x. And we can lump these two arbitrary constants together, just call it c. And that's then is this equals, is the answer for this integral. Now, if y and x both equal 1, then we would have e to the minus t minus e to the minus t up here. So this would be 0. So what we're trying to do right now is evaluate this arbitrary constant of integration. So we'll do it for when y equals 1 and x equals 1. So we'll have the natural log of 1 plus the arbitrary constant of integration will equal, this would just be 0. You have e to the minus t minus e to the minus t. So this equals 0. The natural log of 1 is 0. So our arbitrary constant of integration is 0. So then what we have is it just equals the natural log of y over x. And that's the answer to our problem. So the logic is a little bit convoluted, but here was an integral that we had no way of evaluating it, but we could differentiate it, and then when we go through the differentiation process, we just sort of symbolize that, okay, here's the integral, and it's going to be, it's going to be some function of x. So we just treat it as a variable, and then when we do that, we were able to get an expression for that, which means that we got an expression for this. It was this. This one is almost identical, so the minus ln of x is going to be plus ln of y. So then that gave us the path to getting a solution to our original integral. So here again is another example where we had an integral that we could not evaluate, but by going through the differentiation process using the Leibniz rule that we developed in the earlier videos, then we were able to get an expression for our integral, so we were able to go ahead and solve the problem. We'll have one more example of this in another video that's coming up, and so stay tuned for that. We'll see if we can solve some more problems.